Hello mathematicians, let's have a look at applications of maxima and minima. This is a common type of problem and we've come across it before when we've talked about the maximum of quadratic functions. But now what we're going to have a technique for with calculus is something which will allow us to find maxima and minima of all sorts of functions. So we can do real-world applications. The hardest thing about these problems is not the calculus, it's usually the algebra in setting up the function for which we want to find the maximum and minimum part. So there has to be some sort of procedure which we can apply, and it usually involves reading the problem really carefully all the way through to determine what the variables are, the nature of the problem, and particularly keep your eyes open for the thing which is to be maximised or minimised, because this will give us a clue as to the structure. We need to write an equation connecting the variables, again particularly for the thing to be maximised or minimised, and if we end up with equations with more than one variable, there has to be some sort of linking information so we can eliminate the variables. We can't do our calculus unless we can bring the original equation down to just one variable. Once we do that, we've got an equation in one variable, then the calculus finally comes in. We find the stationary points, which we know is where the first differential is 0, and we determine whether or not they are maxima or minima. If the question has parts within it, then often, if we're really stuck on the algebra, they'll supply us with enough to go on with the question, if it's a decent question. So, we're going to have a look at some work solutions here. In our question, we're after an open rectangular box, so a box with no lid. We're going to cut square corners out of a square piece of cardboard of these dimensions by folding up the sides. And we want to know what the dimensions are to give us the maximum volume. So it's the volume that we're going to have to get an equation for in one dimension. So come to our diagram. Nearly always, if we can put a diagram in, so you'll be well and truly sick of me saying, that will help. So if we cut a corner out of the box of side X, that will leave the dimensions of the box when folded up to be 60 minus 2x by 60 minus 2x. So that means that our volume is going to be height by length by breadth, which is this. And if we differentiate that so that we can find the turning point, it's the product rule. Put down the first, multiply by the differential of the second, which will require a function of a function, plus put down the second and multiply by the differential of the first. Now we can take out 60 minus 2x as a common factor, and that will leave us minus 4x from the first term and one of the 60 minus 2x's from the second term. So we get to this as our expression. Now we can see that to make dv dx equals 0, what we want is either x equals 30, which makes no sense because we'd be cutting corners out which took the whole side of the box, or 10 centimeters. Now to check that we actually do have the maximum turning point, we could find the second differential, but rather than do that, we'll just take some values either side, work out the slope, and we can see that what we're going to get is a maximum turning point. So then go back, read the question. It said what's the maximum volume of the box, not just what is the value for x. So the dimensions to give us maximum volume are 40 by 40 by 10. So that was the process. So we've mentioned it before. Be a stickler for going through in a logical way for these questions, and they won't be so bad. Next one, find the maximum area of a right triangle with this hypotenuse. So we draw our right triangle, mark in the hypotenuse, its area that we want to maximise, so we write an equation for the area. two variables, so there has to be a connection between the two variables. So x and y, when squared, add to 16 by Pythagoras. So if we eliminate y, that means that we'll make it the subject. We put that into our expression here, then we differentiate. And when we differentiate, we've got a product again. So put down the first, the x on 2. Differentiate the second, which is tricky. Remember, it's 16 minus x squared to the half. So that will become a half of 16 minus x squared to the minus a half. So that's why it's on the bottom here. Multiplied by the differential of the function, so that's by minus 2x. Plus, put down the second, multiply it by the differential of the first. As always, when we have a common fraction, we go for a common denominator. So when we do that, then 4 times root 16 minus x squared is what all of these will divide into. So we'll get this and this, because 2 goes into 4 root 16 minus x squared, 2 root 16 minus x squared times. So we gather together the terms up the top and we get this over our denominator. I don't know why the highlighter's not working. We simplify that then to 8 minus x squared over our denominator. So the 8 minus x squared is what we need to equal 0 for a turning point. So that happens when x equals 2 root 2. So when x equals 2 root 2, then what we have to do is to go back and have a look at what the question actually asked for, which was the area of the triangle. So we then plug that back into our equation for area, which was up here. And 2 root 2 on 2 times square root of 16 minus 8 is going to give us eventually 4 square centimetres. And one of these days this highlighter will catch up with what we're doing. So in this question we have point A lying on this curve, and this highlighter's not working yet again. So we have this curve, which is obviously a parabola concave down, as we can see, cutting at 0 and 5. This curve, parabola concave up, cutting at 0 and 3. And by solving the two equations simultaneously, which I haven't shown here, we can get that the points of intersection are 0 and 4, which is why this 0 to 4 has been mentioned up here. So A and B are on the either end of a vertical line because they have the same x coordinates. So the length of AB is just the difference in the y values, which is one of these minus the other, which is 8x minus 2x squared. Now we then differentiate to find the first differential, where that equals 0. So when we differentiate, we'll get 8 minus 4x. That has to equal 0, which is where x equals 2. If we check, because it's nice and easy to get the second differential here, that's minus 4. So we are talking a maximum turning point, so a maximum length as we wanted. And then the actual value of that maximum length we get by substituting back in, and we find that that's going to be 8 units. Our next example is looking at a cylindrical soft drink can. So we draw our diagram as per usual, noticing that radius and height are important, and we've got this fact about volume. First step is to show that the height of the can must be this. So this is just some algebra. Our volume equation for the can, when we substitute our 250 in, is going to give us h is 250 on pi r squared. The second part says show that the total surface area is given by that. So surface area of a cylinder, a closed cylinder, is 2 pi r squared plus 2 pi r h. We've just found h, so we substitute that in, cancel out, and we'll get the expression that they wanted. We want to show that this value of r, which looks awful, gives us a global minimum in the domain r greater than 0. So we want the first differential, just waiting on the highlighter, the first differential, which is 4 pi r minus 500 on r squared. So remember, that was when we differentiate 500 on r. That's really 500 r to the minus 1. So that will be minus 500 r to the minus 2, which is what we have here. And we want that first differential to equal 0 for a turning point. So if we set that equal to 0, that means this is the case. So when we make r the subject of that equation, eventually it's going to give us that r is 5 on the cube root of pi. I'm not going to wait on the pen. So, and then part D says, show that to minimise the surface area of the can, the diameter of the base should equal the height. So that when the radius is that, then our equation for height that we found in part A is going to give us this expression when we substitute r into it, which is 10 over the cube root of pi, which is twice the radius. So have a go at these questions out of 10H. They're slow, but they couldn't possibly be any slower than the pen. So give it your best shot.